336 billion transistors. One chip. NVIDIA just unveiled Rubin, the most ambitious silicon project ever attempted, and it might rewrite the entire artificial intelligence economy in the process. Named after astronomer Vera Rubin, who pioneered the discovery of dark matter, this new GPU platform launches in late 2026, replacing Blackwell as NVIDIA's flagship AI accelerator. To understand Rubin's scale, consider this: Apple's flagship M3 Max processor contains 92 billion transistors. Rubin packs nearly 4 times that, on a single accelerator package. NVIDIA already dominates AI compute, with over 90% market share. Every major lab, OpenAI, Anthropic, Google DeepMind, and Meta, runs on Hopper or Blackwell silicon today. But Blackwell, launched in 2024, was already pushing physical limits: 2 reticle-sized dies stitched together through a high-bandwidth interconnect to act as one giant unified GPU. Rubin doubles down on this approach. Instead of just 2 dies, it uses 4 compute dies and 2 dedicated input-output dies, all linked through advanced chiplet packaging. The architecture is called Rubin Ultra when fully expanded. Single Rubin packages will reach 50 petaflops of dense FP4 compute performance, roughly 2 times the Blackwell ceiling. Memory is where Rubin truly breaks ground. Each GPU mounts HBM4 memory stacks delivering 13 terabytes per second of bandwidth, a 40% jump over Blackwell. Total memory capacity reaches 288 gigabytes per Rubin Ultra package. For context, that's enough capacity to hold a trillion-parameter language model entirely on chip. TSMC's 3nm process node manufactures Rubin's compute dies, using CoWoS advanced packaging to bond compute, memory, and I/O into one massive integrated processing unit. The full system is called Vera Rubin NVL144, a single rack housing 144 GPUs connected through NVLink, behaving as one coherent supercomputer. One NVL144 rack delivers 3.6 ExaFLOPS of FP4 training performance. That single rack matches the entire Frontier supercomputer that topped charts in 2022. Each rack consumes around 120 kilowatts of power. That's roughly the energy demand of 40 average American homes, concentrated in 8 feet of cabinet space. To cool these silicon monsters, NVIDIA now mandates liquid cooling for every Rubin deployment. Air simply cannot remove heat fast enough when over 100 kilowatts pour from one rack. The interconnect story matters as much as the raw silicon. Rubin debuts NVLink 6, doubling bandwidth between GPUs to 3.6 terabytes per second per chip. Between racks, NVIDIA deploys Spectrum-X Ethernet and Quantum X800 InfiniBand fabrics, both upgraded to drive 800 gigabit per second per port across the cluster. Why does this matter? Modern AI training splits one massive model across thousands of GPUs. If the interconnect lags, expensive compute sits idle waiting for data to arrive. Rubin's co-packaged optics, called CPO, integrate photonics directly with the switch silicon, slashing power consumption per bit moved between racks by roughly 3.5 times. NVIDIA's design philosophy treats the entire data center as one computer. Rubin extends that vision to a 250,000 GPU cluster acting as a single unified machine. Software is the secret weapon nobody talks about. CUDA, TensorRT, NeMo, and Dynamo all receive Rubin-specific optimizations months before the hardware ships to first customers. The Rubin CPX variant specifically targets long-context inference. It carries 128 gigabytes of GDDR7 memory, optimized for serving million-token prompts at low cost. Each Rubin GPU integrates a new transformer engine generation, natively accelerating attention operations, the well-known bottleneck inside every large language model trained today. FP4 precision becomes the default for inference workloads. By using 4-bit weights, Rubin doubles throughput compared to FP8, without measurable accuracy loss for production models. Reasoning models like OpenAI's O-series demand enormous inference compute. Rubin specifically targets this workload, where one user query can require thousands of internal token generations. NVIDIA projects 10 to 30 times higher inference throughput for reasoning workloads on Rubin compared with Hopper, measured on the same total power budget. The CPU half of the platform is called Vera, 88 custom ARM cores designed entirely in-house by NVIDIA, replacing the older Grace processors used today. Vera connects to Rubin through NVLink C2C at 1.8 terabytes per second, completely eliminating the PCIe bottleneck found in every conventional server architecture. Vera Rubin systems will ship with full water cooling, redundant power supplies, hot-swappable trays, and built-in telemetry, engineered for 99.9% uptime targets. Hyperscalers have already placed massive orders. Microsoft, Meta, Oracle, Google, and AWS each committed billions of dollars in Rubin allocations before the chip even taped out. Why? Because every additional month of waiting means competitors train larger frontier models. Compute scarcity now directly translates into competitive advantage in the AI economy. OpenAI alone reportedly secured commitments worth over $40 billion in Rubin-class compute, spanning multiple deployment phases through the years 2027 and 2028. Meta plans to deploy over 1 million Rubin GPUs across its Hyperion and Prometheus data center campuses, each campus drawing 1 gigawatt of grid power. And then comes the number that broke the industry. 336 billion transistors. Across one accelerator package. 5 times more than any chip Intel ever produced. Here's what changed everything. A single Rubin Ultra package will deliver roughly 100 petaflops of effective AI compute, more than the world's fastest supercomputer back in 2020. The price per chip? Estimated somewhere between $60,000 and $80,000. Fully built NVL144 racks are projected to cost approximately $3 to $4 million each. NVIDIA's data center revenue, around $115 billion in fiscal 2025, is projected to triple by 2027, driven almost entirely by Rubin platform shipments. The company's market capitalization crossed $4 trillion on Rubin anticipation alone, making NVIDIA briefly the most valuable publicly traded company in all of human history. And here's the kicker. NVIDIA already revealed Rubin's successor. Feynman, due in 2028, promises yet another generational leap built on 2nm silicon process technology. Jensen Huang now operates on a strict annual cadence: Hopper, Blackwell, Rubin, Feynman, with each generation roughly doubling AI compute delivered per dollar spent. The real bottleneck has shifted. It's no longer chip design. It's energy. A single Rubin campus could draw more electricity than the entire city of San Francisco. Nuclear power deals are exploding. Microsoft restarted 3 Mile Island. Amazon bought a nuclear-powered data center site. Google signed deals for small modular reactor power. Rubin's leap is not magic. It is the direct result of vertical integration, designing the GPU, CPU, networking, optics, and software stack as one cohesive product. Most competitors build only pieces. AMD designs GPUs. Broadcom builds switches. Intel makes CPUs. NVIDIA does all of it, optimized end-to-end for AI training and inference. This is why Rubin matters beyond any spec sheet. The lesson is that AI progress now depends on coordinated full-stack engineering, not individual breakthroughs in any single component. Moore's law as a transistor density metric is slowing. But Jensen's law, doubling effective AI performance every single year, is accelerating through architecture and software co-design. Rubin teaches us that compute is becoming a strategic resource, like oil or grain. Nations and corporations now stockpile GPUs the way navies once stockpiled steel and coal. The risk is concentration. One company designs the chips. One company manufactures them. One island, Taiwan, hosts most of the fabs. The entire AI economy balances on this thread. Yet without Rubin, frontier AI development simply stalls. Smaller research labs cannot train trillion-parameter models. Bigger labs cannot serve reasoning queries at scale. The chip enables the era. 336 billion transistors are not just an engineering feat, they represent the foundation layer of the next decade of artificial intelligence, and the global economy built on top of it. Subscribe for deeper dives into the technology defining our future. Drop your Rubin predictions in the comments below.